So basically, we'll start by looking at the fundamental concepts of how a bead works and what happens, and more than just the bead, the binder itself. Um, in this particular case, we're looking at an upper and lower binder surface, which are not down into position yet. There's the bead is not even engaged yet, but when it's fully closed, there should be um, a metal thickness plus. We used to say about 10% of metal thickness. That was common when we were doing 35, 40, excuse me, 40 thousandths thick materials, 0.1 millimeter, maybe point point 0.7 or 0.8 millimeter materials. A lot of our body panels in that are getting down to where they're only about 0.6, excuse me, millimeters thick. And that gets to be a rather 10% of that gets to be a rather small number, only a thousandth or two, and that we're getting to the point where we might actually be close to what the mill variation could be coming as far as thickness. So anymore, although we still leave the 10% clearance between the upper and lower binder, in addition to the metal thickness in there, I began to talk about maybe 3 to 4 thousandths or 0.1 millimeter clearance in addition to the thickness of the metal to make sure that we're not pinching. If I have pinching that happens on the binder, all of those other variables that we talked about early on a couple of weeks ago about lubrication, about cushion pressure, metal thickness, all of those become more and more critical to maintain because a little thicker part with a pinch point is going to create a lot more generation of restraining force. So again, we don't want the binder to be creating the restraining force. The binder's purpose is to keep the metal flat and prevent it from wrinkling. If I get a wrinkle on the binder, now I've not only got to flatten that wrinkle out before I can pull it through the bead, I've also induced some additional work hardening in that part of the material, and all of a sudden the wrinkles will create more restraining force just because they're a stronger portion of the material. They've actually work hardened and the yield strength has gone up. I will also have clearances between the vertical and members of the bead, and also there should be clearance at the bottom of the bead. If I don't have pinching on the binder, I don't want pinching at the bottom of the bead. All of this comes down to I need to have slightly more restraining force than I have draw-in force or forming forces coming from the die. Otherwise, I end up with just pure draw-in and no real stretching in the part, and I end up with a soft panel that can have lows and wrinkles. Okay. Again, purpose of the binder is to keep the metal flat. Don't allow it to wrinkle. Slight variations in inputs, temperature, blank size, and position can cause tremendous changes in the way the panel forms if, in fact, I'm using pinch control. The purpose of the bead is to create the bending and the friction that cause the restraining forces. Smaller radiuses generate a lot more friction, and because the material gets pulled down into them tightly, the tighter that you pull down, the harder you pull down on the material, the more friction you will generate, the more restraining force you will generate. Again, reiterating, flat portion is not allowed, should not be allowed to pinch. As you can see here, there's no reason to have a real tight a condition at the bottom of the bead. The bead can have a tremendous amount of openness at the bottom of it because we're going to bridge from the channel radiuses to the bottom of the protruding bead. And so if I have a little bit of gap below it, that's fine. It's a place for all the zinc that I'm going to rip off the blank to gather, and it gives the die maker something to do to clean the dies between. No, I'm just being facetious, but there's no reason to have a fitted bead or a tight bead at the bottom. Also inside the bead, that clearance of material clearance thickness plus about 3 or 4 thousandths should be maintained. Okay. So again, we're looking at balancing and restraining forces with balancing the amount of force that the die is creating to generate draw-in or forming. If I have an irregular or poorly finished binder, I'm going to have, depending on all of a sudden, if I have a slightly larger blank, if I get out into this area where it's the protrusion is, I can end up with an extreme pinch point and can drive changes. Typically, when we looked at doing die tryout, we would lay out where the blank edge should fall, and then we would actually clear that away beyond that, so that even if we end up with a slightly larger blank, we don't have additional restraining force. Also, if you look at how poorly the shape of the bead is formed, how irregular the channel is formed, each one of those bends will induce an additional restraining force because of the bending and unbending that is induced with it. So the bead does need to be well maintained. It also needs to be properly created as far as the geometries and consistencies. Again, we talked about it should be helped to, if we're using just bead force, it should be relatively insensitive to slight changes. If I have a slightly thicker blank or slightly thinner blank, I'm not going to, I don't have pinch control. I'm really looking at just how much force does it take to bend the material around the tight radiuses, and that's a function of the yield strength of the material, not the cushion pressure of the die. If I've got my equalizer block set, I can have a slight variation in my cushion pressure, and I still won't generate any additional restraining force. How does the again, we talked about the bending forces, and that are a function of the yield strength, where in the formula tonnage for each break, S is the yield strength of the material, T is the thickness of the material, and L is how many linear inches of bead do I have in this die. And this formula, the yield strength times the thickness times the length of the die, tells me how much tonnage I will need for each bend of the radius. So if I have a 4-bend radius, I would take the answer I got here from tonnage per break and multiply it by 4. If I have a 3-bend radius, I would multiply that answer where yield strength times thickness times length by 3, and come up with a amount of tonnage that I need. One of the things that we commonly don't do as die makers or as a die community is, if all of a sudden I decide that I need to add an extra 8 or 10 inches of bead, say above a B pillar or in a window area of behind a C pillar, to create a little additional restraining force. I a lot of times don't calculate in how much additional force is it going to take to set that bead. And this is the formula that should be used to say I've added 8 inches of bead. It's a 3-bend bead. I'm using a 2,000 or 20 KSI material, 20,000 pounds per square inch, and it's a 30 thousandths thick material. Okay, so all of a sudden I might need another 8 or 10 tons of binder pressure in order to ensure that the bead sets all the way. Otherwise, I may end up with a die that doesn't bottom out against the equalizer blocks. And now in my critical areas, I might have a die that's literally opened more than I intended, because I've added additional force requirements to set the beads by adding an additional bead. These are typical examples of what a designed bead would look like, with the draw bead on the left. The entry and exit channel radiuses are designed to start out being the same. And typically, they're going to be somewhere between 3 and 6 times metal thickness, depending on how much restraining force I want. R2, the shape of the actual bead itself, should be somewhere around 6 times the metal thickness. So the diameter of that bead is going to be 12 times the metal thickness, and the height is going to be 6 to 8 times, or 6 to 10 times the metal thickness. Also, the lock bead, or sometimes these end up being what they call a hybrid draw bead, or a 4-bend draw bead. The entry is going to be on the left side, where R1 and R2 are, and they're fairly tight, only twice the metal thickness. Okay. Also, the exit side of the male bead, that radius is going to be about 2 times metal thickness. R2, again, we've talked about it. If there is any metal thickness, not only is it going to be used to restrain material, but also that's the radius that's going to absorb most of the load from the material trying to be drawn into the die. So we don't want that radius to end up almost working like a trim cutting edge. So we make that one slightly larger so that it can transfer a slight amount of the load into the vertical component between the R2, R1 radius. So that slight draw wall there may get or bead vertical wall may get stretched just a slight amount, but R2 is a little bit larger because of the forces it will receive from the attempt to draw material in. And again, height is only going to be 6 times the metal thickness, and the width of the bead is going to be approximately 12 times metal thickness. Okay. Again, these are preliminary guidelines as things begin to happen and tryout works in the die shop. They will work those radiuses a little bit to match the draw in that the original design intended. Okay. Thinking about what happens to the material as it gets pulled through a draw bead and actually slides through this bead. On the left-hand side of the screen, we see the blank edge, or that would be the outer edge of the blank. That's the original yield strength of the material. As the material gets pulled into the die at the first bend, we get a bending and we actually get some work hardening. It wraps around to the tangent point and then literally gets straightened back out or unbent as the material moves towards the bottom of the male bead. At the unbend area, we also get additional work hardening. So the material that's being pulled around the male portion or the protruding portion of the bead is stronger than the initial yield strength. So to bend and unbend it around the bead, we're actually dealing with more material, which that is stronger, has a higher yield strength. It comes out of the bending around that bead, going back up the vertical wall towards the second channel radius. We have stronger material that gets bent around the third bead or the third bend in the radius. And so I'm dealing with much stronger material there. And so consequently, if I were as a die maker to have to make a slight adjustment where I wanted to have more material draw into the die, I would go in and I would grind a slight change in the radius size of the exit side of the channel. Because that material is already doing far more of the work it's dealing. That radius is working with harder material. It's actually generating more restraining force. Having said that, as a die maker, now that means that I probably should disassemble the die, set the die up on a set of sawhorses, and actually work from the inside of the die. It's much easier to get a good fit, a good finish, consistency if I'm working from the inside of the die. The outside radius is very, very tempting. I can walk up to the die, I can grind it, I can change it, and not have to disassemble the die. I will just have to clean the die after I've done my work. But now I've taken a die portion that is working with soft material, and I'm not only going to change how much that material gets work hardened there, but I'm going to send softer material into the second die radius and also into the third radius. So a small over grinding on the initial outside radius is going to have potentially a very, very large adjustment to the amount of drawing I get. Also, the inner radius is now even doing more of the work than the outer radius, and the wear will and erosion of that radius will become more exaggerated as time goes on.